So folks, as I said at the start of these pre-work videos, my goal is to cover the last two major topics for the course, and then we'll in class start to flesh out all the details to those. So right now I want to look at the second of those topics, which is solving differential equations with what's called the Laplace transform. So in the next few sections we'll look at how to compute these Laplace transforms. And what we'll do is we're going to compute Laplace transforms of functions and then translate IVPs, initial value problems, into an algebraic equation. We then hope to, once we've converted the differential equation with its initial conditions into an algebraic equation, we then hope to invert the solutions to those equations back into IVPs. So here's the idea. We've got an IVP that we want to solve, and we're trying to arrive at the solution to it. And we've learned a lot of means to try to get, from that IVP to a solution. But what will happen a lot of times is we're going to get stuck. So what we do instead is we're going to convert that IVP into an algebraic equation. Our goal is to then solve that and then translate that solution back to a solution to the original IVP. So the process of taking an IVP and transforming it to an algebraic equation will be done under the method of taking the Laplace transform of that of the ODE. So we'll take the Laplace transform of the ODE back into this space where we will come up with an algebraic equation. We will then solve that algebraic equation, and then we will do the inverse transform of the solution to that algebraic equation, bringing us back to the solution of this IVP. We will get into more detail as we go through the course, but that's the general model of what we're doing with these Laplace transforms. So what is the Laplace transform? Well, if we have a function f of t defined on this interval right here, so it's got to be defined for non-negative values of t, then the Laplace transform, which we will denote this way. So I'm going to use this script curly L, and then we use braces around the function that we're taking the Laplace transform of, is an integral transform given by, well, if we take the Laplace transform of some function, f of t, the way we're going to compute this is by taking the integral from 0 to infinity, that's why we need it defined on 0 to infinity, of our function. But what we're going to do is we're going to multiply this function by e to the minus st dt. Now, this s is going to be the variable that we now solve our algebraic equation in terms of. So a lot of times what you'll see here when we do these problems is you'll see this space right here referred to as the t domain, and then you'll see this space referred to as the s domain. And I really don't want to, especially in this introduction video, get into what I mean by the t domain and the s domain. But instead what I want you to think of is we're going to take from one space, we're going to take our initial value problem, convert it over to another space through the Laplace transform. That will give us an equation that we solve, and then we invert back to get to the solution. And so the Laplace transform, the mapping that takes us from time domain to s domain, is this calculation right here. Notice that when we integrate with respect to time, that our solution to this will only have the variable s in it after we're done integrating with respect to time and then evaluating the limits of those integrations. Okay? So let's make one other comment, that this isn't just any old transform, that the Laplace transform is linear. Okay? And by that I mean if we were to take the Laplace transform of some constant times the function f plus some constant times the function g, so a is a constant, f is a function, b is a constant, g is a function. If we were to do this, then from our definition above of the Laplace transform, this would be the integral from 0 to infinity of a f of t plus b g of t times e to the minus st dt. But then by the ability for the integrals, when we have convergence, to distribute over sums of functions, and our ability to factor out constant multiples from integrals, I can rewrite this as a times the integral from 0 to infinity of f of t e to the minus st dt plus b times the integral from 0 to infinity of g of t e to the minus st dt. And what have I shown? I've shown that this is equal to a times the Laplace transform of the first function plus b times the Laplace transform of the second function. Okay. So we're going to make use of the linearity of the Laplace transform all the time, which is why I need to show it even in this introductory video. And that linearity says we can pull out scalar multiples to a function, and we can distribute the Laplace transform over sums of functions. Of course, that doesn't hold for other operations of functions. So in the next video, what I'd like to do is pick up by actually computing the Laplace transform for the function e to the 7t, and to do so, we're going to have to use this definition. By the way, I want to finally add to this. I should have added provided the integral converges. So folks, I'll see you in the next video where we actually compute this Laplace transform, and then eventually we're working up to the goal of solving an initial value problem with the Laplace transform. So I'll see you in the next video.